Alright, in this video, I'm going to be talking about finding the area between two curves, except this time we're going to be talking when these curves are expressed as functions of y. And there's really two reasons why we'd need to do this. The first is the more obvious, like I just said, x is a function of y, and that's the first one we're looking at right here. X equals 12 minus 3y squared. X is given as a function of y. We're going to need to find that area. We could probably work around and solve for y, but then we'd have to deal with some square roots, and who knows what we would have going on there. We don't really want to do this. This is actually going to be pretty easy if we integrate on y. So what we're going to do is we're going to turn our rectangle sideways, okay? We've always been doing Riemann sums, adding up areas with vertically oriented rectangles, but there's no reason we couldn't do them horizontally. So I'm going to draw a representative rectangle just like I did on the other areas. And I'm going to say, okay, on the left I've got x equals 0, the y-axis, and on the right I've got x equals 12 minus 3y squared, the curve that they told me about. Okay, so I'm going to go off to the side and just like I did before, I'm going to say, okay, this is my representative rectangle. Okay, the width of this rectangle, it's going to be right minus left. And I know I haven't really explained why that is, but, hopefully you've already seen top minus bottom. So this, process should seem familiar. On the right, I've got x equals 12 minus 3y squared. On the right, I've got x equals 0. So top minus bottom is now right minus left is 12 minus 3y squared. Okay, but then the question is, like, what do I do with these intersection points? Like, how do I even find those? Okay, and that's just like before. I'm going to set two things equal to each other. If they're intersecting, they've got the same x-coordinate, so 0 equals 12 minus 3y squared. And that's something I could solve for y. Okay, I think just by looking at it, right? 12 minus 12 is 0, so 3 times 4. Okay, that's going to be y equals 2 or negative 2. So we're going to label those spots. Okay, now I'm going to go in and I'm going to compute an integral to find the area of region R. So this area is going to be an integral, and I'm going to let these rectangles slide up and down, these horizontally oriented rectangles slide up and down the y-axis as y runs from negative 2 to 2. So this will be my balance of integration. And then I'm going to be adding up these rectangle areas. So I need to think about a height and a width. Okay, so I'm going to, in parentheses, it's actually going to be the width, because that's what depends on y, and the height is going to be dy, because it's a really short rectangle. The height is very small. So my width is right minus left is 12 minus 3y squared. My height is dy. Okay, so I'm going to compute this integral. I'm going to take an antiderivative for 12, and I would get 12y. The antiderivative for 3y squared would be y cubed. And let y go from negative 2 to 2. And then I'm going to plug in these bounds of integration. Okay, 12 times 2, 2 to the third, 24 minus 8, that feels like 16. Minus, and then when I plug in negative 2, I'm just going to get the exact opposite thing I got before, because the antiderivative is an odd function. And so I get negative 24 plus 8. And so I get 16 minus negative 16, that's going to be 32. All right, and just like I did in the last video, I'm going to draw you 2 points and suggest we think about the horizontal distance between these 2 points. Okay, they have the same height, right, the same y-coordinate. We would find that horizontal distance by taking the difference in the x-coordinates. We would take x2 minus x1, right minus left, and that would give me 5. If I moved these up, that would not make sense. If I moved these points up and one of them was to the left of the y-axis, I'd still be taking right minus left to find that horizontal distance. That distance would be 1 minus negative 4, and that would still be a distance of 5. And if I moved them once again so that both of the points were to the left of the y-axis, I would still be getting this horizontal distance by taking right x-coordinate minus left x-coordinate, and that would still give me the same 5. So in general, when we're finding a horizontal distance, that's why we're going to be taking right minus left, or x2 minus x1. And now going back to the original situation, the other reason why we would need to integrate with respect to y is a little bit more subtle. Now this shaded region on The bottom half of the screen here, this is one that we could potentially find with x. We would need to use two integrals, right? Because top and bottom does switch. It goes from line on top and line on bottom to line on top and curve on bottom. Okay, but the main obstacle for us at this point in our course is that we don't have an antiderivative for natural log x. We could not find this by hand. Okay, but if we find this with integrals in y, it's actually quite easy. Okay, so I'm just going to say we don't have this antiderivative yet, so that's going to motivate us to integrate with respect to y. Okay, so I'm going to kind of label region S and see what's going on here. So I've got this curve here, and this is y equals natural log x. Now, on the other one, we already had x written as a function of y. And if we're going to write our integral with respect to y, we're going to need to solve for x. Okay, so that's where we're going to say, oh, y equals log x. How do I solve for x? Oh, I take e to both sides power. So I'm going to say, okay, x equals e to the y. And then I'm going to label the left edge of S, and that would be just x equals 0. Now thinking about the other two parts of the boundary of S are those horizontal lines, like y equals 0 here and y equals 1 up there. Those are going to become my bounds of integration. Okay, now, thinking about the representative rectangle again, just like always, okay, it's going to sit sideways because I'm going to integrate with respect to y. I'm going to take it off to the side and think about the width of this rectangle. It's going to be right minus left. It's the difference in two x coordinates, x2 minus x1. On the right, I've got x equals e to the y. And on the left, I've got x equals 0. Okay, so that means that my width is going to be e to the y. And so to find my area, I'm going to integrate as y goes from 0 up to 1 on width times height. So width is e to the y. Height of that rectangle is dy, and now I'm ready to compute the integral. Okay, it shouldn't be too hard. Anti-differentiate, plug in the bounds, subtract, get e minus 1. We're good to go. Okay, now here's another one. This one's a little different. Maybe we kind of got both of the same things going at the same time. But this is one that we would really want to with respect to y to make our lives so much easier, right? Again, we probably could do it with respect to x if we knew how to anti-differentiate log x, but man, curve versus line curve, this would be a whole lot easier to turn a rectangle sideways like this and, integrate with respect to y. That's getting worse, I feel like. Okay. All right, so if I take my rectangle off to the side, on the right, I've got y equals log x. Well, that's x equals e to the y. And on the left, I have y equals square root x, so that would be x equals y squared if I was to solve for x, square both sides. Okay, and so now the width of my rectangle is going to be right minus left, and the height would be dy, so the area is going to be the integral of e to the y minus y squared with respect to y as y runs from 0 to 1. And, we could compute that the rest of the way, but you've seen me do a lot of these integrals recently, so I'm just going to show you the work and maybe move on from there. Okay, now pretty much the only other thing I can think of that we could do with this is like, okay, the line y equals k cuts the region into two equal areas. Set up an equation that we could use to solve for k, but I don't think we're going to actually be doing that here in this video. I did one of those in the integrating with respect to x video. Okay, so I'm going to say, well, we've got two things that are going to be equal, two areas. So I'm just going to set two integrals equal to each other. Okay, now the first integral is going to start at y equals 0 and end at y equals k because it's the lower half of that kind of green striped region. And then the other one will be as y goes from k up to the top of the region, which is y equals 1 on the same thing, okay, right minus left, because that's not going to change. Okay, so, and the right minus left, oh, look, it's the same as it was before, so that'll be e to the y minus y squared. And I don't think I even mentioned in the other video when I was integrating with respect to x and using Desmos occasionally, but those parentheses actually do really matter on the calculator if you're using Desmos to compute these integrals. But if it just says set up and do not evaluate, then we're not going to need to do anything more with this because this is expressing the two equal areas thing. And I recognize there are other ways that you can set this up. You could say the integral from 0 to k is half of the integral from 0 to 1. Or 2 times the integral from 0 to k. I mean, there's just like all sorts of ways you can set it up with addition. I don't know why you would do that, but you could. There's all sorts of ways, and they're all equivalent, right? If you think about the integrals equivalent to the areas, all that stuff. Okay, so I think that's all I got to tell you for this video. Yeah, I don't have any other examples, so that's all for this one. Thanks for watching.